Okay, so let's say that this is the mass of fluid that we want to conserve. But after, and we want to conserve it in time. You see that I wrote the balance equation in differential terms against time. So during time, I want to conserve it. And why during time? Because the process, the variable that I want to describe, the river flow, is time varying. So if I want to describe the progress of the river flow over time, I have to conserve the mass of fluid in time. Okay, perfect. So, but after a time dt, this body of fluid moves, and it's here. This is a problem, because actually, I want to balance, conserve my mass of fluid in the catchment. And the catchment is fixed. So the volume of fluid, which I want, whose mass I want to conserve, is moving. And you see that I cannot say that I want to conserve the fluid here, like when I am in the catchment. I have to conserve a mass of fluid that is moving, so the volume is traveling. So basically, the volume of whose mass I want to conserve travels, but I want to compute the mass balance over a fixed volume, which is the catchment. So this is a problem. And we need a theorem that allows us, not a theorem, let's say a theorem in this case, but we need a trick that allows us to keep the volume fixed. So we need to pass from a volume of fluid that is moving to computing the balance of fluid in a volume that is fixed. And in order to do that, we need to use this theorem. And now I'm trying to explain it to you. It is very simple in practice. In practice, it's very simple, as you will see. And the purpose of the Reynolds transport theorem is to pass from the computation of a balance over a volume that travels in time to pass to the computation of a balance in a volume that is fixed. This is the purpose of this theorem. And as I said, in principle it's very simple. When we will see the application, it's very simple. But actually, you need it. And what's interesting is that this transport theorem can be applied to balance any thermodynamical property. So not only the mass, but also the energy, the heat. I say thermodynamics. Thermodynamics is a branch of dynamics which considers not only the movement of the bodies, but also the transformation of mass and through an exchange of heat. And therefore, any thermodynamical property, heat, energy, momentum, mass, can be balanced by using the Reynolds transport theorem, which is nice, I mean. So basically, when you, in hydraulics, you study the continuity equation, what is the foundation of the continuity equation? It's the Reynolds transport theorem. When you study the conservation of energy, Bernoulli theorem, what is the basis of the Bernoulli theorem? Reynolds transport theorem. So any, again, thermodynamical properties of a moving fluid can be balanced through the Reynolds transport theorem. And when I speak about thermodynamical properties, let me distinguish between intensive properties and extensive properties. So, what's the difference? Let me make an example. If I have a glass of water, let me consider the temperature. The temperature is an intensive property. It means that even if I took half of the glass of water apart and I make another measurement, the temperature remains the same. So you understand that the intensive property doesn't depend on the volume of the considered fluid, moving fluid. Another intensive property is mass density. So if you take a glass of water and you split by 2 and you measure the mass density of the water in the 2 sub-glasses, it's of course the same. Let me now provide an example of an extensive property, the mass, not the mass density, the total mass. So if I compute the total mass of water inside a glass, and then I split it in 2 parts, if I compute on the 2 parts, the total mass is changed, of course. So the extensive property depends on the volume of fluid that is considered. In this representation of Reynolds transport theorem, the extensive property is identified with the symbol capital B, the intensive property with the lowercase b. So this is extensive, this is intensive, which means that given that we refer to a volume of fluid that is moving, basically capital B is the total extensive property of the moving fluid. So if I consider, for instance, as intensive property the mass density and as extensive property the total mass, the total mass is indicated here with capital B, the mass density with lowercase b. Okay, now what is the left-hand side of this equation? It's the changing time of the extensive property for the considered volume of fluid that is traveling. In our case, the fluid is water. This volume of water that is moving, capital E is, for instance, the total mass of this volume of water that is moving, and the left-hand side is the changing time of the total mass of this volume of water that is moving. In many cases for us it will be 0, because if you don't have any mass change, it's 0. But it's important to note that this is the total, total derivative. The total derivative in time of the considered extensive property like total mass of the moving volume of water. Okay, fine. Now, how can we express it? Because what we want to do is indeed to balance this quantity. It may be the total energy, it may be the total mass, but we want to balance this quantity for our volume of moving water. So how can we express it? This is our purpose. As I said, in many cases we put a 0 here. If we want to write the conservation of energy, we put a 0 here. But our purpose is to write it for a fixed volume. Now, let's turn to the right-hand side. At the right-hand side, you have the partial derivative in time of what? Of an integral extended to the fixed volume. V is now our fixed volume. The catchment, for instance. And therefore you compute an integral over the catchment of what? The product of the intensive property, mass density for instance, times the mass density of the fluid. Rho is the mass density of the fluid. Here you still see a mistake that I corrected in the slides that you can download. Here R should be rho, is the mass density of the fluid, and dV is the incremental variable of the integral. So basically, what do you do over the considered volume? You simply take the intensive property, you subdivide the volume in infinitesimal part, and for each of them you take the intensive property and multiply them by the mass density of the fluid. Fine. And what is this in practical terms? In practical terms, you can consider that this may be a source term. So let's suppose that within your catchment, you have indeed a rainfall. Rainfall causes, inside the catchment, an increase of mass and an increase of energy of the water. And you consider it through this term. It's an integral over the volume of a source term of mass or energy. Okay? If you don't have any rainfall over the catchment and you don't have any other water losses, this term could be zero. Okay? Good. Now, let's look at the second term. The second term is representing the fluxes of the considered property through the surface, the boundary of the volume. So you may have, for instance, over a catchment, some fluxes through the boundary, like underground flow, and then you have to consider them, because you know, you may have these contributions, or in a pipe, for instance, you may have if your fixed volume is the whole piece of pipe, you have water entering into the pipe from the cross sections, and you have to consider them. Sometimes it's not so easy to split these two terms, these two contributions in source term and fluxes through the surface, because if you think of a catchment, for instance, rainfall would be considered also a flux through the surface of the catchment. If you consider that the atmosphere is lateral surface for the catchment, of course rainfall could be considered also flux. And or for the case of the pipe, if you have a contribution from the boundary, water entering into the pipe, usually you consider it as a flux, not as a source term, because clearly you have in this case a flux of water entering from the limiting surface of the pipe. But if you had, for instance, like an injection here, an injection, some people may represent it as a source term, other people may represent it as a lateral flux. And usually, you know, I prefer in these cases to consider it as a source term, because if it is a lateral flux, it means that then you have to consider also an energy component, because it's entering with a given velocity, and therefore you have to consider it also its energy component if you consider it as a flux. So I prefer in these cases, when I represent a catchment and I have, for instance, a river inflowing into another river, usually I consider it as a source term. But what's important to see here is that this change in the extensive property, you may represent it as the sum of two contributions, a source term inside the considered fixed volume and flux through the surface S of the volume. And this flux, you can write it in this way. Again, the intensive property, again, the density of mass of the fluid, and then you have to consider the velocity of the flux times the outgoing normal unit vector through the surface ds. So you see that in order to consider this contribution as a flux, you also need to know the velocity of the entering fluid. Okay, now it's a bit complicated. I understand it's a bit complicated, but what I just want to emphasize from the practical point of view is that basically what you need to do to compute your balance equation in terms of energy, in terms of mass, is to identify the fixed volume over which you want to compute that balance. And in our case, this fixed volume is the catchment. And you may say the catchment is a surface, not a volume. No, indeed, when you make this computation, you have also to consider the underground. So even if we identify the catchment as a surface, when you compute the mass balance or the energy balance, you have to consider also part of the underground, so it becomes a volume. So the catchment in this is a surface, but when I compute the balance, I use the term computing the balance over the catchment, and implicitly I should imply that the catchment is defined as a volume. And the way in which you define it as a volume is to consider the catchment surface plus a portion of the underground. And basically, this volume over which you identify, over which you compute your balance, we call it the control volume. Okay, so you have to identify a control volume. Again, it can be a pipe, it can be an aqueduct, it can be a city, it can be a catchment. And then, inside this control volume, you have to compute the fluxes through the boundary and the source terms. The source terms may be, for instance, the water demands, because it's a water withdrawal, so it's a negative source term. So the water demands, I represent them through this integral over the volume, and if I have instead fluxes entering into the catchment, I represent, or the aqueduct, or etc., I consider them through the second component. So this is what you have to consider, to compute the balance of mass and energy over a fixed volume, source term and fluxes. Okay? We could easily derive this continuity equation from Reynolds transport theorem, and let's don't do that, because I don't want to insist on this basic theory. What I kindly ask you is to learn by memory this mathematical equation, and to learn how to explain it. And this is a question that I may ask you if I realize that you are very good. Okay, I told you that I have some tough questions that I use in order to make a difference. And I never start with this equation, with this question, but at the end of exam, if you are very good, I may ask you, do you remember how to write the Reynolds transport theorem and what it means? What it means is important to me, but also the mathematical relationship. I won't ask you to learn by memory many equations. That's why I kindly ask you to learn it. Okay, if you need any, I just would like to move forward because I don't want to insist too much with complicated concepts. If you need any clarification, just let me know. Okay, so you see here, this is a watershed with the divide. And we have this problem of identifying the runoff given the rainfall over this watershed. So let's go back to our practical problem. And let's try to introduce some simple models. Probably you already know them. And the first one, first of all, here you can find some slides that describe what is a watershed with more details. They have different form and size. And let me see if there is something else. Here you can see how to identify the divide by using a topographical map. I'm providing these slides because I want to give you some information, but this is something that it's not interesting for me because I assume that you have already the necessary preparation by the necessary background in order to identify the divides over a topographic map. But here there is some information. Here there is a scheme that I already shown to you, and I already projected. And basically, with the mathematical model, we pass from physical system to a mathematical system. And now let me make some, give you some information. And this is something that I consider very interesting, even if it's not very mathematical. You should learn how to guess the behavior of a catchment by looking at the behavior in terms of runoff, how it can behave after a rainfall, basing on your experience. So this preliminary guess that you can elaborate by experience is extremely important. And what I mean with experience, it's a bit personal. I don't think that the experience of a professional or a technician is proportional to the time that she has dedicated to the considered job. Experience to me, because usually we say an old person is experienced. I don't think so. Even a young person can be very experienced. Experience means knowledge. And experience means that you know, in my view. And you know because you studied. So a person can be very old, but if he didn't study and he didn't observe, he is not experienced. Or a person can be young, but he observed a lot and experienced a lot. I say it's an experienced person. So to me, an experienced engineer may have 35 years or even less than that. Because you know, the experience again means that you elaborated through observation and through the studying activity, you elaborated the capability to gain a preliminary understanding of what's going on. This is extremely important, because then you compute, you pass the computation, but your preliminary understanding, your preliminary guess is extremely important. So when you go to a building that was damaged by an earthquake, you see, you look at the cracks, you look at the behavior of the building, and you gain a guess of what's going on, and then you make your computation. You see the beam, if they are wood beam rather than iron beam, and then you make your computation. And you expect that your computation confirms your guess. If you see that something is not matching, then you wonder what was wrong. And it can be your preliminary guess, but it can be also the computation that is wrong. So to me, an engineer should gain the capability to get a confirmation of the results that he gets, because an engineer applies the result in practice. So if you make a mistake, it's not just a mathematical mistake. It's a mistake that can imply the death of people. So a good engineer should gain the capability, as I said, to get a confirmation of what he derives by using theoretical principle. And the way in which you confirm your computations is your preliminary intuition, your preliminary guess. So if you move to hydrology, very often we are called to solve problems related to floods, related to drought, to water resources management. It's extremely important your capability to go over a catchment, to look around, and to gain a preliminary guess of what's going on. So, to make a very stupid example, if you see a very green catchment, you guess, oh, it must rain a lot here. If you see a dry catchment, your guess is either it doesn't rain much or it's very hot here. And of course, this is very simple. But, or if you look at the catchment and you see that there is a relevant erosion and no water in the river, then you guess that there is an extreme variability in the river flows. So the river is dry, but if you see relevant erosions, it means that in some times of the year, the river flow is violent, has a relevant energy in order to erode the catchment. So these are all guesses that are extremely important. And therefore it's what's the reason why I projected before this size, form of the catchment. It's extremely important that you gain a guess. Sometimes, very often, we are called to estimate the peak flow. And a good professional, just by looking at the catchment, looking at its size, looking at the rainfall, is capable of gaining a guess. And I will give you some indication for this. But the first indication that I give to you, if you are interested in gaining this experience in hydrology, you have to start looking around. Every time you see water, try to understand how the water moves, where the water comes from, and everything. Or if you see an hydraulic work, like if you go over a river and you see a barrier, start wondering what's the purpose of it. And start wondering whether it was well designed or not. Start asking people. And it's extremely interesting. The opinion of people is, I would say, never reliable. But by listening to people, you learn what's going on. It's extremely important. And so basically, if you look at this hydrograph here, first of all, the hydrograph is a reaction to rainfall. So here you see what we call a yetograph. The diagram of rainfall along time is called the yetograph. If you look at the yetograph, you start learning when it rains, if you have heavy rainfall or not, if there are long dry periods. If you see a long dry period with no rainfall, you start understanding that water resources management is a problem there. Because if people are living there and there is a long drought every year, it means that they have stored water somewhere, otherwise they can't get any water during summer. Or if you see, this is not, this is enough detail. If you see a graph like this one, you see that there are no long dry periods. And this is the monthly rainfall. You see, this is an ideal situation for water resources management. Every month you have rainfall. There is only one exception, which is very strange here. But every month, almost every month, you see you have good rainfall. And the rainfall is not much varying. And probably this is observation from 1 year only. Let me see, it's 1 year only. So this is why there is this month with no rainfall. So another thing that you have to learn, 1 year of observation is too short. I told you 10 years, it's a rough indication that I give in order to get a reliable understanding of the hydrological regime. So in this case, this year is still significant because it tells you that in this location, basically, they got rain this year every month. So either it's an exceptional year or it's a good location because it means that these people get water every month. The yetograph. Here you see an example, the yetograph is the graph of rainfall. The graph of the river flow over time is called the hydrograph. Okay, and the hydrograph, if you look at an hydrograph, you gain a lot of information for catchment. Let me give you an example. If you look at, for instance, for the Po River at a flood hydrograph. So you take the hydrograph, which means time on the abscissa and river flow over the ordinate. You look at it and you see that the peak flow of the Po River, the peak hydrograph is something like that. And the base time, this is the base time of the flood hydrograph, is about 1 week. So if you get a flood over the Po River, it lasts for about 1 week, maybe more, not less. Once that you get a big flow, you are in trouble for about 1 week over the Po River. So you see this hydrograph, you don't know anything. First of all, here you look at the discharge and you see about 10,000 cubic meters per second. Okay, let's suppose that you didn't know this peak flow. Just by looking at the hydrograph shape, you understand, oh, this must be a huge river, because the base time of the hydrograph, 1 week, must be a huge river. If you look at the flight hydrograph of a very small river, it lasts for about a couple of hours. So the hydrograph is like that, very peaky, and the base time maybe 1 hour. And then I say, oh, this must be a very small river, very small catchment, sorry. In this case, I say, this must be very large catchment. And when the catchment is very large, usually you have a very long rising limb and a very long falling limb. And if I look at the river flow, you know, I look at 10,000, I say, oh, this is a really huge catchment. 10,000 cubic meters per second means that the catchment is really huge. Instead, in this case, where the hydrograph is 1 hour, this could be something like 15 cubic meters per second. And if I see 15 cubic meters per second, I say, okay, this is very small. Probably with such a big flow, I would say this catchment probably is less than 1 square kilometer. Instead, with 10,000, I would say this is at least 50,000 square kilometers. And how do you gain this information? Just by looking at that. If you go over Google and you Google hydrograph, you get flood hydrographs for plenty of rivers, almost any river. If you go on the website of the United States Geological Survey, they have plenty of hydrological data. And you could look at the flood hydrograph of the Mississippi and the flood hydrograph of very small rivers. And you can learn what is the order of magnitude of the flood hydrograph, the length of the flood hydrograph for a huge river and a small river. And what will you see? You will see that for huge rivers, the contribution per unit surface of the catchment to the flood flow is much, much lower than for small river catchments. I say again, you will notice that the contribution per unit area of the catchment to the flood flow for a big catchment is much, much lower than the contribution per unit area of a smaller catchment. I give you an example. And let's refer to the river flow that happens on average every 100 years. For the Po River, the area of the catchment is 70,000 square kilometers, and Q is about 15,000 cubic meters per second. So look at here, 70,000 square kilometer of area of the catchment, and the peak flow, with peak flow I mean the flow that occurs on average every 100 years. The peak flow is about 15,000. So if you compute the lowercase q, which is 15,000 divided by 70,000, this is about 0.2. About 0.2 cubic meter per second per square kilometer. This is the unit contribution to the peak flow of this catchment, or specific peak flow. It's also called specific peak flow. Okay, now let me make another example. The Secchia River. The Secchia River is a river that is located in this region that flows from the Apennines, is much smaller than the Po River. And the area is about 1,200 square kilometers, and Q is about 800 cubic meters per second. So if I compute lowercase q, this is 1,200 divided 800. I did, sorry, a mistake here. I should divide 800 divided by 1,200 which is about 2/3, so it's about 0.67 cubic meters per second per square kilometers. You see the difference, 0.2, 0.7. For catchments of 10 square kilometers of extension, you may find specific contribution of about 10 cubic meters per second per square kilometer. So the smaller the basin, the higher, the smaller the catchment, the higher the specific contribution. And you may wonder, why is that? And this is something that could be interesting if I didn't tell you and I asked you in the final exam. But I prefer to tell you. And because it's intuitive, you can easily guess why is that. Because if you have a huge basin and it rains in one part of the catchment, it's very likely that it doesn't rain over the whole catchment. So you get contribution to the runoff only for a limited part of the catchment. If you have a very small catchment, it may happen that it rains over all the catchment. So you have a much higher contribution. This is one first reason why you have a higher contribution. And there is another reason which I want to explain to you, because also this second reason is more difficult to guess and helps you to better understand hydrology. So if you think about a very huge river like the Po River, in your opinion, this flood that may occur